All right, let's get started with volumes of prisms and cylinders, section 12.4. Our lesson objectives are to find volumes of prisms and cylinders and use these volumes of prisms and cylinders. Our essential question, how can you find the volume of a prism or a cylinder? All right, let's establish some key terms here. Our volume is always the number of cubic units contained in the interior of a solid. Cavalier's principle helps us understand that if two solids have the same height and the same cross-sectional area at every level, then they have the same volume. So that means if I pick a different cross-section, the area of the cross-sections will be equal. So no matter what level I choose along the height, the cross-sections of the two shapes have the same volume. So that leads us to one of our key formulas. So the volume, capital V, of a prism, any prism, is capital B times lowercase h, where capital B is the area of the base and h is the height of the prism. Again, height is the distance between the bases. Remember, the base area is always dependent on what shape the base is. All right, so let's find the volume of each of these prisms. Start with part A. Part A is a triangular prism, and we know that because the bases are triangles. Again, your bases are the unique shapes of the prism and parallel to each other. So let's identify what formulas we'll need. So I always start by thinking about the master formula, which is volume in this case, so capital B times that h. And I know that my base is the shape of a triangle. That's my next step. So because it's a triangle base, then the area of a triangle formula needs to be in my workspace. So half of B times H. Now this B is not to be confused with the capital B. They are different values. They represent different parts of the prism. Also, same for the lowercase h, not to be confused with these two formulas. They are not the same values. So for the triangle shape, just the triangle is our focus. So its base is 4 and its height is 3. So those are the numbers I plug in and get a area of the triangle to be 6 centimeters squared. Therefore, capital B is 6. So I will use that value in my volume. And then I know that the height of my prism is 2. So 6 times 2 is 12 cubic centimeters. All right, let's take a look at our B prism here. It's a trapezoidal prism. So my bases appear to be trapezoids. Again, they're the unique shapes that are parallel to each other. So I like to identify the formulas I will need within my workspace. So my master formula, the volume, capital V times lowercase h. So that means I need to identify my base shape, and my base shape's a trapezoid. So because my base shape is a trapezoid, that's the area that I need to, formula that I need to use for finding capital B. So 1/2 height times base 1 plus base 2. Again, this is only for the trapezoid base, two-dimensional. So I identify all my parts. So the height of the trapezoid only is 3, not to be confused with the trapezoidal prism's height, which is 5. That value will be used over in this formula for this h. This h is for the base only. So h here is 3 centimeters, b1 is 6 centimeters, and b2, base 2, is 14 centimeters. So I plug in all these numbers in the right places. So 3 goes in place of h, 6 in place of b1, 14 in place of b2, order of operations. So we get 1/2 of 3 times 20, which is 60. So half of 60 is 30 square centimeters. So that means our capital B is 30 square centimeters, and that's what we will plug into our master formula. And then our height of the prism is 5. So 30 times 5 is 150 cubic centimeters. All right, so let's consider finding volume of a cylinder. So let's consider a cylinder with a height h and base radius r, and a rectangular prism with the same height that has a square base with sides of length r times square root of pi, as illustrated here. The cylinder and the prism have the same cross-sectional area, which is pi r squared, at every level and the same height. So by Cavalier's principle, mentioned earlier, the prism and the cylinder have the same volume. And the volume of the prism is capital V equals BH equals pi r squared h. So the volume of the cylinder is also V equals capital BH equals pi r squared h. So that leads us into the volume of a cylinder. Remember, the volume of a cylinder is capital B, lowercase h. Now remember, when you're replacing capital B, you have to first identify the shape of the prism. So the base in this case is a circle. So capital B gets replaced with pi r squared. Height is still the height between the bases, the distance between your bases. All right, so let's consider using our new formula. It's the same formula as far as BH, but in place of B, we have a different formula. All right, so our volume formula, capital B times H, and capital B is getting replaced with pi r squared because that's the area of a circle, which is our base. So we'll use a radius of 9 feet and a height of the cylinder to be 6 feet. So first, let's find the area of the base, which is 9 squared, 9 in place of r, which is 81 pi. We'll just leave it exact, and that's the value we will plug into our master formula. So we get 81 pi times 6, which results in 486 pi cubic feet for exact, and then approximately 1,526.81 cubic feet. So for example B, also a cylinder, it's oblique. We still use the same formula, pi r squared h. So radius is 4, height of the prism, remember it's the vertical perpendicular distance between the bases, always, even if it's oblique, and that's 7. So plug into our formulas. To get area of the base, we'd have 4 squared, which is 16. So the area of the base only is 16 pi. Use that in our master formula for capital B, and then the height of the cylinder is 7, and that comes out to be 112 pi cubic feet exact, and then approximately 351.858. All right, let's take a look at modeling with mathematics. You're building a rectangular chest. You want the length to be 6 feet, the width to be 4 feet, and the volume to be 72 cubic feet. What should the height be? All right, so the formulas we'll be dealing with is the master formula, which is for volume, so capital B times lowercase h, and we have to know the shape of our base. So our shape this time for the base is a rectangular shape. So we know that area of base formula is going to be length times width. So that's where we'll start with a length of 6 feet and a width of 4 feet. We have the area of our base being 6 times 4, which is 24 square feet. So that means capital B is 24 square feet. So we're going to use that 24 for our master formula. So we put it over here in our list. And since we know the volume, we do not know the height of our prism. We know the volume of our prism is 72 cubic feet. So that's going to be in our list of things we'll use. So in place of capital V, I put a 72. In place of capital B, I put a 24. And I'm solving for this h. So that means I need to divide both sides by 24. And as a result, I get h equals 3 feet. So the height of the chest should be 3 feet. All right, for the first time, we're going to see how changing dimensions in a solid affects volume. And that means we have 3 dimensions that are affected. So we're going to describe how doubling all the linear dimensions affects the volume of the rectangular prism. So we'll start with the before change. So our dimensions are, the length is 4 feet, the width is 3 feet, and the height of the prism is 6 feet. We know that volume is multiplying all of that together because the area of the base would be 4 times 3, and then the height of the prism is 6. So multiplied together, we get 72 cubic feet. So after the change, doubling all of the dimensions, we get 8, 6, and 12. And plug this into our master formula for area of base, we would get 8 times 6 times 12, the height. So multiplying all that together, we get 576 cubic feet. So next we want to compare the new to the original by dividing. So doubling all the linear dimensions results in a volume that is 576 divided by 72, or in other words, 8. If we convert that to involve exponents, 8 is equivalent to 2 cubed. Well, 2 was the original factor that we used to double all the linear dimensions. So that 2 is very important. And then the 3 power is the number of dimensions that changed. So I can always take my scale factor that I'm changing my dimensions by, and whatever number of dimensions are changing, that's my power. So if I give you no picture and no other information, I can always use this information to go from an original volume to a new volume for any 3D object. So let's see how tripling the radius affects the volume of the cylinder. So before we change, we have a radius of 3 and a height of 6. Plug that into our volume formula for a cylinder, so pi r squared times the height of the cylinder. So 3 squared, which is 9, 9 times 6, which is 54. We'll leave it exact. And let's compare to after the change. So we're only changing the radius, not the height. So only one dimension is changing. So we get a result of a volume of 486 pi cubic centimeters. So let's divide the old volume and the original, the original and the new. So divide new by original. So tripling the radius results in a volume that's 486 pi divided by 54 pi, which is equal to 9, which is equal to 3 squared times the original. So because we only changed one dimension, the power is 2. Not all dimensions changed. And because the radius changed, then that affects the area. So area is squared. That's why the power is 2. And our last example we want to look at is a composite solid, getting the volume of composites. So first, let's consider our situation. And we know that we'll need multiple formulas here. So ultimately, we will need the volume of the concrete block, which means we need capital B times the height of the block. So let's think through what we would need to do to get area of the base. So capital B is going to be the area of the large rectangle minus 2 times the area of the small rectangle. Because if I just look at the base, I've got the large rectangle and then I've got 2 cutouts, 2 small rectangles that I need to cut out. So let's consider the parts of the large rectangle and then parts of the small rectangle. That should say small right there. We don't have both of them large. So this one's going to be parts of the small rectangle. Alright, so parts of the large is going to be 1.31 feet for the length and 0.66 feet for the width. So that's the full large rectangle here, as indicated 1.31 and 0.66 feet as indicated here, and these edges are parallel. For the small, we've got a length of 0.39, and then for the width we have a 0.33. So we're going to plug in to our formula over here. To get area of the large, we take length times width, and then we need 2 small rectangle areas. So we plug in all our numbers, and we get an area of the base being 0.607 square feet. So we're going to use that over here in place of our volume formula, because we know the height of the block, the cement block, is 0.66 feet. So our area of the base times the height of the block gets us a volume of 0.401. So the volume is about 0.401 cubic foot. It's not even a full 1 foot, just part of a foot. All right, and that's all for this lesson. See you in class.